Hello and welcome to today's topic. We're looking at binomial distributions, and our goal today, I can identify the appropriate time to use and successfully apply binomial distributions. And that's going to be the trick here as we move further into this unit. You need to be able to identify the different types of distributions, and you got to know how to use them successfully. So you're going to see in the example today, and as we progress, how it does get a little bit more challenging. Quick history lesson. This binomial distribution was developed by a gentleman named James Bernoulli, famous mathematician, and dabbled in physics a little bit. And it was referred to as the Bernoulli trials. And what it is, it's a mathematical process that determines the probability for an experiment with only two outcomes. So binomial distributions. We know this, the Bernoulli trials as this, and here are the conditions. These conditions must be met in order for it to be binomial distribution. So what I would recommend is that you want to put this on your cheat sheet somehow, and you can shorten it up however it works. But it's very, very important being able to answer these questions. So for an experiment to be a binomial distribution, the following conditions must be met. Not a combination, all. All of them have to be met. So you're asking yourself, first of all, are there n identical trials? So is each trial the exact same? The second one, there are only two possible outcomes, success or failure. So if we're dealing with a sum of a dice question, for example, and there are 7 outcomes or 10 outcomes, this does not work. You can only have 2 possible outcomes, and we have to be able to identify one as success and one as failure. The third one, the probability for success is the same each time. So if there's a 30% chance you win the first time, there has to be a 30% chance you win the second time, and so forth. So the probability has to stay the same, so there has to be replacement, and the trials have to be independent. So that's talking about replacement. If I'm pulling socks out of the drawer, I have to put my sock back before I do the next draw. So those 4 conditions absolutely must be met. Formula for the binomial distribution. So we're still using our probability notation. Okay, so the probability of our random event occurring, a random variable, equals x. We are looking at the formula with n. So we're doing combination notation. So you're going to have to find that combination button on your calculator. P to the exponent x, q to the exponent n minus x. Now to simplify that formula, let's give you a legend to work with here. So I'll just group this and just slide it over here. So off to the side. And keep in mind, this is a combination. So you have to use your combination button on the calculator. All right. We have n, which is our number of trials. Number of trials. X is number of successes. And I will put in brackets the word successes, because I'm going to talk about that a little bit. Successes is whatever we're hoping to get out of it. So technically, if we want to know what's the probability of something failing, failure in this case would be our success. So success is a relative term. So it's not so much a positive result, it's the result that we're interested in. P is the probability of success. And Q is our probability of failure. All right, and keep in mind, this goes back to Unit 1, P plus Q is always equal to 1. It's always 100% something's going to occur. Okay, expected value formula then, same notation, EX equals, and this one's a little bit easier actually than the previous one. It's just N times P. And those values, the N and P, come from that legend as well. So it's just number of trials multiplied by your probability of success. So there is our 2 formulas that we will be using in this section. So example, If a coin is tossed 15 times, determine the probability that you toss exactly 10 heads. So just quickly going through the mental checklist. Okay, N trials, I'm just going to shorten this up. Okay, ident. So flipping a coin, yeah, the trials are identical. 2, success or failure. Yep, you can either get ahead or not ahead. 3, same probability. Same probability each time. Yep, it's always a 50-50 chance. And finally, independent. And yes, if I toss a head, the coin doesn't care what it does the next time. It could be a head or a tail. So that's kind of the mental checklist that you're doing, especially when we introduce other probabilities and they start getting mixed in. So it's important that you go through that mental checklist. The other thing I want to point out with this one, thank God it said exactly. Because if it said at least, you would have to do a table for 15 trials. I'm not overly keen on doing that. So because it said exactly, we can use this formula right here. What is the probability that our random variable is going to equal 10? If it was greater than or at least, then it becomes a process of creating a large table. So we're fairly lucky in that. So what's the probability that we get exactly 10 heads? So 10 is the success criteria in this case. So I'll put down here, success is equal to a head. How many trials are we looking at here? We're looking at 15 trials. What's the probability of success? P, 50-50 chance, 0.5. What's the chance of failure then? Also 0.5. So when I go to fill out my information from the formula, I am looking at 15 choose 10. My probability of success is 0.5 to the exponent 10. My probability of failure would be n minus x. So in this case, I'll put the 15 minus 10. So now it just becomes a task in using your calculator. So this saves us from doing a huge tree diagram. It saves us from doing a graph or tabular form. We can just punch this in. So 15 choose 10 times 0.5 to the exponent 10 multiplied by 0.5 to the exponent 5. And I get 0.092. So therefore, there is a, however you want to report it, 9.2% chance of getting 10 heads on 15 flips. All right. So this is when it's exactly. Exactly is always the situation you're hoping for. If it doesn't say exactly, then you're going to have to create a table. So, second example here. In class, probably Mr. Egger is in a bad mood is 5%. Really can't see that. Over a 2-week period, so 10 days, determine the probability that Mr. Egger will be in a bad mood exactly twice, at least twice, and determine how many days you can expect him to be in a bad mood. Again, very, very rare. I would say this example is a little bit skewed, but that's all right. So A part, exactly twice. So, in fact, what I'm going to do is I'm even going to take it back a little bit further. Okay, is it a Bernoulli trial? So in your head, you're thinking to yourself, is it the same probability every time? It looks that way. It's 5% bad mood every time. So that's the same. Okay, success or failure. It seems like I'm either in a bad mood or a good mood. So that tells me that there's no in-between. So yes, it's part of a Bernoulli. Independent. There's nothing stating that yesterday's mood affects today's mood. And so there we go. So writing out our information. Total number of tests here. There is 10 days that we're looking at. Probability of success is 5% or 0.05. Now keep in mind, over here, what's a success? In this case, it is a bad mood. So that is what is considered a success. So here's this. Success is not necessarily a positive event. It is the event that we are interested in. Q is 0.95. So again, be thankful you see that word exact. Exactly is very, very important for us. So, A part then. Probability of success for exactly 2 is equal to 10 choose 2. Our probability is 0.05 to the exponent 2, 0.95 to the exponent 10 minus 2, or just 8. So calculating that, so 10 choose 2 times 0.05 squared is 0.95 to the exponent 8. And I get 0.0075. So the probability that Mr. Agar is in a bad mood is 7.5%. There is a 7.5% chance it occurs exactly twice. Okay, so that's pretty good. I'm happy with that. 7.5% chance happens twice. That sounds about right for me. B part, at least twice. Now you're thinking, oh no, here's the word at least, or words at least. So one way to handle it, P of x at least twice would indicate it would be greater than or equal to 2, which means I would have to do 2 plus 3 plus all the way up to 10. Not really what we want to do because that's a lot of work. So let's look at it the opposite direction. Let's try indirect. Okay, indirect. So doing the opposite. So we know that the probability adds up to 100%. So the probability of it being greater than 2 would be equal to 1 minus the opposite, the probability of it being less than 2, and not equal to, just less than 2, which would mean we'd have to do 1 minus.
Please remain seated till the bell.
So this way we can look at the probability of x equaling 0 minus the probability of x equaling 1. Because again, we don't have to worry about 2. 2 is in the other one. So 1 minus. So we would have 10 choose 0, 0.05 to the exponent 0, 0.95 to the exponent 10, minus 10 choose 1, 0.05 to the exponent 1, 0.95 to the exponent 9, and we would calculate that value in order to find out this at least part. And we get 0.086, so 0.086. So therefore, there is an 8.6% chance of being in a bad mood. At least 2 times or twice. And I will finish the last part of this example up in the final video and finish up the note.